The sky is a vast ocean of mysteries, an endless frontier humanity may never fully uncover. Since ancient times, people have likened the stars to gods. Since ancient times, people have likened the stars to gods. Yet, these were only myths, not truths. When science rose to prominence, it pulled us out of the dark ages. We began separating myth from reality, seeking instead to explain the cosmos through the laws we could uncover. And yet, as science advanced, something remarkable happened. The ancient stories of gods began to echo back to us, in ways far more real than we could ever have imagined. Could it be that everything ultimately points toward a single conclusion, that somewhere out there, beyond the veil of stars, there truly exists a supreme force, a higher being who designed it all? When we speak of genius, names inevitably come to mind: Newton, Einstein, and even Tesla. Yet no matter how brilliant they were still human, and humanity is never without flaws. In his years of studying and unraveling the universe, Einstein made profound predictions, visions that propelled humankind further along its journey to unlock the mysteries of the cosmos. But alongside those triumphs came mistakes. Mistakes that even Einstein himself would later admit were the most foolish moves he had ever made. To understand this greatest blunder, we must journey back to a time when Einstein was not yet the legendary scientist we know today. This was the moment when Einstein's theory of relativity was first unveiled, and the scientific community did what it does best: refuse to accept it. The very essence of science lies in testing and experimentation. Instead of trying to prove something right, science strives to prove it wrong, and only when a theory cannot be broken does it endure as truth. This relentless, almost maddening process marks the fine boundary between real science and pseudoscience. For true science must be built upon laws and principles, never upon the flimsy explanations of coincidence. Therefore, when Einstein proposed the theory of relativity, something with the potential to overturn the entire body of science since Newton, the scientific world was extremely strict, trying to test it in every possible way. And then, through each calculation and each experiment, Einstein's relativity gradually appeared as the victor when set against Newton's laws. One of Einstein's greatest victories came when scientists applied Newton's laws of motion to Mercury. According to Newton, an object moving in a vacuum without any external influence would not change its speed or its direction. Mercury, moving through the vacuum as it orbited the Sun. This means its orbit should never change. But strangely, Mercury's orbit does shift over time. Meanwhile, Einstein's theory of relativity proposed that space and time are one, and together they form a stage upon which matter performs. In essence, the Sun is a massive body that bends this fabric of space-time, causing other bodies, specifically the planets, to fall into its well. And just like objects drawn into a whirlpool, the orbits of the planets cannot remain fixed. From this, the mysterious orbit of Mercury could finally be explained. And in fact, the same applies to the orbit of every other planet in the sky, something Newton's laws still struggle to carry. In short, Newton's laws could describe quite accurately the motion of matter in the universe, but Einstein's theory explained the very core of that motion. From there, it could be used to predict the movement of matter in the vacuum of space. Einstein's relativity did not go against Newton. More precisely, it completed his work. And from that point on, scientists gradually came to accept relativity as the foundation of astronomy, of space science, and as a framework that could be widely applied across many fields of research. But this is where the problem begins. If Einstein's theory of relativity were truly the perfect model of the universe, where matter bends spacetime and creates gravity, then wouldn't the universe collapse in on itself? More precisely, if gravity were the only force at play, wouldn't the universe be contracting instead of expanding? After all, the universe began more than 13 billion years ago, and if gravity alone had ruled over everything, then across those billions of years all matter should have clumped together into a single massive body. Instead of galaxies, stars, and dazzling nebulae, the cosmos would be nothing more than a vast, silent black hole, devoid of life. And yet, here we are, stars still shine, nebulae still paint the heavens. So, was Einstein's theory of relativity wrong? To deal with this issue, Einstein introduced a concept, the cosmological constant. Written into his equations with the symbol lambda, this constant acted as a counterforce to gravity. Its existence implied that gravity would not be able to pull all matter back together. In other words, this constant pushed matter away from its original position, an effect opposite to gravity, keeping the universe in a static state. It sounded profound, almost elegant. But in truth, the very idea of this constant made it seem as though Einstein had simply invented it to cover up a flaw in his own theory. Why should there be a force that runs counter to gravity? The existence of this constant ignited a new debate about the laws of the universe. Perhaps relativity, like Newton's laws of motion, was still incomplete. Or maybe, in all these brilliant calculations and predictions, we overlook the most important truth, that we are only human and this universe is far too vast to be confined within our small equations. Perhaps Einstein was right, that some mysterious force prevents all matter from collapsing into one. But perhaps he was wrong, and the cosmos is far greater than the reach of his formulas. And no matter which is true, science remains science. Its greatest duty is still to experiment, to question, and to search for answers. And now the question becomes, if the universe is not static, as Einstein once proposed, then what is it? Einstein's theory of relativity had, perhaps unintentionally, introduced an assumption that the universe was static, that all things would simply orbit one another for eternity, and nothing could ever disturb the vacuum that preserved this perfect balance. To maintain such a picture, Einstein introduced the cosmological constant to counteract gravity. But this was neither the first nor the only time someone imagined a static universe and analyzed it in depth. Long before Einstein published his theory of relativity, many scientists had already looked up at the heavens and asked, why must everything be static? A question so simple that we might ask ourselves why we did not doubt it from the very beginning. Perhaps we were all deceiving ourselves, believing that the universe must be perfect because it was the creation of God, that everything must exist in a flawless state just to satisfy our human intellect. But reality has always lived beyond imagination. Ever since the brilliant mind of William Herschel, the German-born musician turned astronomer, discovered infrared radiation in the year 1800, the world has never been the same. Other great minds built upon the concept of infrared radiation to uncover the entire spectrum of light, from what can be seen to what cannot. Light, like all waves, has its frequency, and that frequency determines its color. The visible spectrum ranges from red to blue, meaning from low energy to high. In other words, the higher the frequency, the bluer the light; the lower the frequency, the redder it becomes. When light grows so strong that it surpasses the visible spectrum, it becomes ultraviolet, or UV rays. Stronger still are X-rays, which we use to scan the human body. Beyond them lie gamma rays, harnessed by scientists to destroy cancer cells. On the other end of the spectrum lies weaker light, so faint the human eye cannot perceive it. This is infrared radiation. Weaker still are microwaves, and at the farthest end, radio waves. The shift of light is used by astronomers to measure the distance and velocity of celestial objects. If the light appears blue and flickers strongly, it means the object is approaching us at a terrifying speed. If it appears red and flickers weakly, it means the object is moving away from us. In 1912, American astronomer Vesto Slipher discovered a spot of light in the sky with rather peculiar characteristics. It was blue, meaning it was moving toward us, but the intensity of the blue light indicated an extremely fast and dangerous approach, at a speed of up to 300 kilometers per second. At such a tremendous velocity, this light could not possibly belong to our own galaxy. And indeed, it didn't. It turned out to be an entirely different galaxy, the Andromeda Galaxy. In the years that followed, his research revealed that many other galaxies were also racing through the universe at astonishing speeds. By 1921, a galaxy called Drea had been discovered, and it was moving away from us at a speed of up to 2,000 kilometers per second. Too many galaxies were flying everywhere in the universe, each with different directions and speeds that were not uniform at all. Why could galaxies move like this? If the universe were static, then they should follow fixed orbits, right? Slipher was not the first, nor the only one, to look up at the sky and accidentally uncover evidence of a dynamic universe. In 1922, Russian astronomer Alexander Friedmann expanded on Einstein's equations and suggested that the expansion of the universe was entirely possible, and that we could even calculate its rate of expansion. Then came Edwin Hubble, an American astronomer, who brought clarity to the story. Hubble measured the distances between newly discovered galaxies and our own, and then compared them with the redshifts of those galaxies from Vesto Slipher's earlier research. From that comparison, Hubble unveiled the nightmare hidden beneath the universe's beautiful veil. Distant galaxies were redshifting faster than those closer to us. This meant that the farther away an object was, the faster it was receding. But this did not imply that we were at the center of the universe. Instead, it revealed that space itself was expanding. Everything was drifting apart, with the separation accelerating over time. In 1929, Edwin Hubble quickly published his discovery so that other scientists could witness the true nature of the cosmos. Among them was Einstein, who now faced undeniable evidence laid out before his eyes. He could no longer continue defending his cosmological constant. In other words, his vision of a static universe had collapsed. Einstein's misstep from that point on became legendary. a reminder that even giants in science have their moments of downfall. However, this mistake did not mean the world turned its back on Einstein. On the contrary, it became a monumental step forward for global science. Now, we had two fundamental forces shaping the universe: Einstein's gravity and a mysterious, almost demonic force pushing everything apart. Where there is mystery, there is brilliance. Scientists threw themselves into studying the gaps of the cosmos like moths drawn to a flame. Why was everything drifting apart? That question burrowed deep into the minds of astronomers, compelling them to propose temporary explanations such as dark energy and dark matter to account for this ghostly phenomenon. Yet this was only the beginning. The universe is far too vast and profound for us to claim we have grasped its full picture. Somewhere out there, countless questions still await us, taunting and challenging us on our journey to trace the ultimate origin of all things. And this is the very question that neither Einstein nor Hubble could ever have foreseen.